is by Roland Farrell. He will be talking about digital quantum simulation of scattering and quantum field theories using states.
Okay, hi everybody. I'm Roland. I'm a postdoc at Caltech. Thank you for the good opportunity to talk at this workshop. Today I'll be telling you about some exciting progress on simulating high energy particle collisions using quantum computers. So the motivation for this work is really considering the kind of scattering or collision events that you would find in a high energy particle collider, such as the LHC. So there they have lead nuclei, which they accelerate up to very close to the speed of light. Kind of a cartoon of the process is you have these different nuclei, they move towards each other, they collide, they explode, quarks and gluons go everywhere. And it's kind of an interesting theoretical problem of what's produced after this collision. It requires understanding kind of out of equilibrium dynamics in the standard model particle physics. And this is something that we think is really beyond classical computing, really doing these simulations from first principles. But we believe that this is something where we can simulate the quantum field theories directly on the lattice. This can be done efficiently if we had access to a sufficiently powerful quantum computer. That's kind of the goal that will underpin what I'll talk about today. So I'll briefly have two different parts. So first, I'll tell you about this new quantum algorithm that we have for preparing the initial state in these scattering simulations. These are called wave packets. And then I'll tell you how we use this new algorithm to actually simulate inelastic scattering using IBM's quantum computers. Inelastic scattering is when you collide particles at high enough energies that you actually turn some of the kinetic energy into additional particles in this case. And the details on this work can be found on this preprint from May. So first, I'll tell you about this new algorithm. So in these high energy collisions, the initial states are these wave packets of single particles. And I'll tell you more about what these wave packets are, kind of define them more precisely. But what I want to convey is that this is kind of an interesting question of how to prepare these wave packets on a quantum computer. And previous works had been quite good by both myself and some other people. But they had a shortcoming, which is that if you look at the required circuit depth to prepare these states, they scaled extensively with the volume of the wave packet that you wanted to create. In some cases linearly, in other cases polynomially. And this kind of precluded near-term demonstrations because the circuit depth that you would need would quickly kind of exceed your error budget. I should say there's some other competing methods that incurred an exponentially growing classical computing overhead. And the nice thing that we were able to show is that we can actually reduce this to being just an order 1 depth, allowing you to prepare these very large wave packets in a circuit depth that doesn't grow with the size of the wave packet. And the reason that we want to be able to prepare these large wave packets is that this gives us a really high precision probe in terms of determining what is happening at a specific momentum or energy. And that's what we're going to need to be able to understand kind of different scattering channels in these high energy collision processes. I should say, if anyone has any questions, please interrupt me at any time. Okay, so more precisely, the kind of wave packets that we'll be considering are these Gaussian wave packets. These are wave functions that saturate Heisenberg's uncertainty principle. So uncertainty in x times uncertainty in p is bounded by h bar over 2. This is kind of the best object that we can have that both has a well-defined position and a well-defined momentum. As a wave function, it looks something like this. So the key here is these psi k's. These are like single particle plane waves with some momentum k. And if you add them together in this superposition weighted by a Gaussian momentum space, then you're able to create an object that's localized both in momentum space around some momentum k0 and also localized in position space. This is kind of how the wave function would look like on a lattice. It would have this nice Gaussian shape where the width is set by 1 over sigma p and it moves with some momentum specified by this k0. Our goal is to prepare this state. That's what we're going to need in order to simulate the scattering that I'll talk about. And a kind of immediate problem that you run into is that it turns out these wave packets have long-range entanglement kind of over distances set by the width of this wave packet, which is in turn telling you how precisely you can target things in momentum space. And this is essentially because if you look at the wave function, it's like a superposition of a particle being at different sites, where these sites are kind of weighted by this Gaussian envelope. But if you know a particle is here, then it cannot be there. And so this is kind of creating entanglement that's existing over a large region. And because it's long-range entanglement, you know that if you had a unitary circuit, you need at least a depth that scales linearly with the volume of the wave packet.
How important is it that you have like finite number of qubits and finite spectrum in K and everything? Does it impose any restrictions on how large the circuit should be?
So it's going to set like the maximum width of a wave packet that you would consider. But all these things, as you take your lattice size to be larger, you get kind of more fine-grained in momentum space, and so these effects seem to mostly wash away. Okay, so kind of the high-level strategy is, first we want to find circuits that prepare this long-range entanglement that's over this wave packet volume. And the key thing here is that if we have access to circuits that have mid-circuit measurement and feed forward, we can actually do this in constant depth. We compare this long-range entanglement in constant depth. For people unfamiliar, this MCMFF is kind of a more generalized version of quantum circuits where you can apply some unitary gates and then measure some qubits, and then based on the measurements, feed forward some additional gates and act as more unitaries. This allows you to kind of implement a non-unitary process, and in this case, allows you to spread long-range entanglement more efficiently than if you only had a unitary operation. And then the second step is, okay, we've kind of built this long-range structure of our desired state. Now we need to get the short-range structure correct. And this involves building correlations over the size of a correlation length, which in our case is going to be proportional to the inverse mass gap. And one of the nice things is we show that this can be reformulated as an energy minimization problem. And so we can actually find the circuits that get these short-range correlations correct by using a variational quantum algorithm that is minimizing the energy subject to some additional constraints that I'll tell you in a second. And this is nice because these variational quantum algorithms find usually very compressed circuits for doing a given task that just relies on some optimization. So this method for wave packet preparation is quite exciting because it seems to be pretty general. We tested it in a lot of different candidate lattice field theories, both in 1 and 2 dimensions. But for the rest of this talk, I'll tell you just about this simple 1 plus 1D Ising field theory, just because it's the easiest to explain, and it's also the one that we actually ran on the IBM hardware. So I'll tell you about that part too. So what is the Ising field theory? It's defined by a Hamiltonian, which just looks like this mixed field Ising model. So it's in 1 dimension. You have a ZZ coupling between nearest neighbor sites. You have a transverse field with strength Gx, and you have a longitudinal field with strength Gz. And it turns out there's a field theory that emerges at long distances when you go towards the critical point, which is taking Gx goes to 1, Z goes to 0, with this funny ratio of the couplings held fixed. This ratio is obtained by looking at relevant deformations to Ising CFT. But what's important to know is that this defines actually a whole family of quantum field theories. So perhaps the most familiar one is if you just take Gx as 1 and Gz as 0, I'd be over here. This is an integral field theory. This is just a free Majorana fermion. Kind of in the other limit, if Gz is large, but you're taking this limit, then you actually get another integrable field theory called E8 theory, discovered by Lomolodchikov in 1989. But in general, you can take this limit with various ratios held fixed, and this actually defines kind of a continuum of interacting and non-integrable field theories that have non-trivial S matrices that we can probe by scattering these wave packets together, and that's precisely what we'll do. Okay, so the first step of this wave packet preparation was really trying to build this long-range entanglement in the wave function. So the way that we do that is we start with some state which actually has the right long-range entanglement. In particular, we start with the state that we call this W of K0. This is a superposition over a computational basis states with a single 1 in them. And the weights of these C coefficients are kind of specified by the Gaussian wave packet you want to construct. Their magnitude follows the Gaussian. So if you just looked at like where the ones are and what the amplitude is, it would look a lot like the wave packet you want to prepare. And the key thing is that in the wave packet that we want to prepare, the long range entanglement between positions of these particles or positions of these excitations is really the same as the entanglement between positions of the ones in this W of K0 state. So this state actually kind of has the long range entanglement that we need. And in fact, the really great thing is that this kind of state has actually been studied a lot in the quantum information community. Because if you set all of these C coefficients to be equal, this is precisely the W state, which has applications in quantum sensing and also in quantum key distribution. So we're going to be able to leverage kind of some existing methods that people have come up with for preparing these W states. So in particular, if you only had a unitary circuit with 1D connectivity, then it's easy to show how you can have a circuit that has linear depth in the size of the wave packet you want to prepare. This is essentially, the fact that it's linear depth is telling you that it has this long range entanglement. But then it turns out that if you have all connectivity, you can improve this to be logarithmic depth. That's already a pretty big improvement, exponential improvement. But then it turns out that if you have 1D connectivity and you also have access to this mid-circuit measurement and feed forward, you can actually do this in constant depth. And so this is how we were able to kind of reduce our wave packet preparation to just being constant depth. And this is really kind of generalizing and building off of this paper from last year by Droley et al. Okay. So that's the first step of this wave packet preparation. The second step is to try to build this short range entanglement or building the correct correlations over the correlation length. And to kind of motivate how we make this into an energy minimization problem, I want to think about how does the Hamiltonian look like? So on a 1D system with periodic boundary conditions, our system has translational invariance. So we know that in momentum space, our Hamiltonian is block diagonal, where every block is kind of specified by the momentum, discretized in units of 2 pi over L, where L is the system size. So there's some familiar states here. If you look at the lowest energy state in the momentum 0 block, this is precisely the ground state or the vacuum. And it turns out that if you look at the states in a block that has non-zero momentum, these psi k or these single particle states with momentum k that we want to prepare inside of our wave packet are exactly the lowest energy states of these blocks with k not equal to 0.
So when you have this W state, it's the zero momentum Fourier transform in the one particle set.
So usually it's shifted away from the zero momentum. There's no overlap with the zero momentum part.
So
Oh, sorry, the W state is a zero momentum.
yeah, so the one particle states are size n.
Yeah.
So these blocks are they are in the one particle states or they are in the general.
No, this is all in like the many body Hamiltonian,
When
but there's going to be n of these blocks because there's n different lattice
it's
momentum.
a 2 to the n matrix.
Yeah, yeah. But then kind of more generally, if we look at excited states in these blocks, they could be multiple particles of different relative momentum. But because we can identify these psi k's as being these lowest energy states, it kind of motivates that perhaps there is a way of rephrasing the state preparation in terms of energy minimization. And that's exactly what we're going to be able to do. So kind of if we first start with this W of K0 state, which had the correct amplitudes in the different momentum sectors and had the right long range entanglement, then it turns out that if you minimize the energy subject to the constraint that your circuit onsets is both translationally invariant and also real, that you're actually preparing the desired wave packet. And the reason for this one is that this kind of preserves the amplitude of your state in these different momentum blocks. And so it ensures that it's projecting down onto this single particle vector. And it turns out you need this constraint too, because there's some phases that you need to make sure don't get screwed up. So kind of more formally, the energy minimization problem looks like the following. You start with this W of K0 state. You act with some parametrized circuit or unitary U of theta. Then you minimize the energy. this the unitary that minimizes the energy is this U of theta star. And you can prepare this target wave packet state with this U of theta star acting on W. Yeah.
The number of angles is linearly proportional to the system size in this case?
No, it's independent of system size. So it's actually going to be more proportional to the correlation length.
Okay.
Essentially, because we have this translationally invariant
That's a small-
structure, yeah, it makes sense. Okay, so kind of at a higher level, this is how it looks like. You prepare this W of K zero state, it has the right momentum structure, but maybe has the wrong particle content. Then you do this symmetry preserving energy minimization. You kind of project this down onto wave packets of single particles. And it turns out that actually the optimization problem is really simplified because you have these symmetry constraints, because it kind of constrains the structure of the circuit you can search over and makes it so the number of variational parameters doesn't grow with system. So just briefly, we did state vector simulations on 28 qubits. We see that indeed minimizing the energy kind of maximizes the fidelity. This works. And we're actually able to also do this optimization using an MPS circuit simulator on system sizes of 100 plus qubits. And again, this works. So this kind of concludes the first part of the talk. We're going to use these circuits we found with the MPS simulator for preparing these wave packet states, to prepare them on the quantum computer, and then time evolve on the quantum computer using trauterization to simulate scattering. Okay, so 2 minutes, so I'll go really quick. So in the Ising field theory, the parameters we choose, there's kind of two different particles, a light one and a heavy one. They'll be denoted by a blue circle.
We have 7 minutes. 7 minutes.
Okay, then I'll go slower. Okay, so the next part of the talk will be I'm doing a utility scale simulation of this inelastic scattering using IBM's quantum. So again, this Ising field theory Hamiltonian looks like this. For the parameters that we choose, it turns out there's two stable particles, a light one that we denote by this little blue circle, and a heavy one with this red circle. And the scattering process we want to see is we collide two of these light particles, and kind of after the collision, we produce one of these heavy red particles. So we can do this already with matrix product state simulations or MPS simulations. Because this is a 1D system, we can actually simulate the dynamics pretty well. So what this is it's a space-time diagram where the lattice sites are on the horizontal axis, time is on the vertical axis, and the colors are denoting energy density. So this is showing on the left-hand side elastic scattering process where the energy of these initial wave packets is below this inelastic threshold. And you see that these beams of particles go in, they collide, and you also get two beams going out. This is just kind of characteristic of an elastic scattering process. But then on the right, if we increase energy past inelastic threshold, we can actually see that the two particles go in, but then outgoing, we see this additional beam of energy. This is corresponding to this new heavier particle, which is actually traveling slower. And so the goal of our quantum simulation is going to be, can we kind of start to see signatures of this new particle being created in this post-collision state? Okay, and then this is kind of a complementary view of a simulation of this. So we start with these two wave packets that are these Gaussians in energy density at time 0. Then we time evolve, they kind of come together. You get this peak from the collision, and then they move apart. And what you'll notice is that as they move apart, you start to see this additional bump emerge and become more and more sharpened. This is this additional particle being produced after the collision. So jumping forward to the results from the quantum computer. So these we ran on IBM's device, IBM Marrakesh. We found a 104 qubit chain of qubits that we used that are shown here. And we repeated these simulations for 4 different time slices that are kind of shown overlaid on top of the MPS simulations here. So at time 0, we just have these nice Gaussian wave packets. At this T1 of 8.25, this is in the middle of the collision. So we see this kind of peak in energy density. And then as we start going to later and later times, we start to see kind of what's happening in the post-collision state and start to see the initial formation of this heavier particle too. Couple things to note is that This latest time required close to 5,600 2-cubic gates and a gate depth of 130. This is kind of similar to what Roland was saying earlier about pushing kind of the maximum of what we can get with these current devices. And you also notice that kind of systematic errors start to creep in between the MPS prediction, this gray dash line, and then the results from the quantum computer, the points with error bars. So what we ideally want to do is get to even later time where it's very obvious that we have this additional particle produced and we can see kind of a clear bump in the energy density. But we can't do this because already at this earlier time, we were starting to get a lot of noise. So this was kind of the furthest we could proceed in the simulation. So then have we actually seen any evidence of this inelastic scattering, even though we're not at this kind of asymptotically late? And we think that we actually have. And the way that we diagnosed this was by looking at the asymmetry or the skewness of this bump in energy density that we obtained from the quantum computer. So essentially, this energy density, it becomes skewed because you have this additional particle in the wave function that's traveling slower, and it kind of drags out the tail. So this left column is showing results from this scattering simulation at the 2 post-collision times. And this skewness metric gamma kind of gets larger as you go to later times. This is kind of consistent with MPS and due to this inelastic particle production. But we also see that the skewness gets contributions from noise. I mean, there's pretty significant systematic errors here. So how do we know that what we're seeing is just not due to noise? And kind of the way that we diagnosed this was by running an additional simulation where we just had a single particle propagating. And this simulation should have very similar noise to the full scattering simulation, but have less skewness because there's no inelastic effects going on. We repeated a simulation of just a single particle propagating, and we found that it's kind of significantly less skewed than the 2-particle collision. This is giving us evidence that at least some of these, some of the skewness is actually due to this inelastic particle production. Okay, so with that, I'd like to kind of summarize and conclude. So I think there's kind of 2 interesting questions. One is more theoretical, which is this long-range entanglement that we found in these wave packets and built from these W states. Is this kind of a universal feature that all single particle wave packets, if we look at their long-range entanglement, it can be kind of classified as a W state? We don't know. And then kind of another interesting question is, well, can we actually expect there to be a quantum advantage in scattering kind of in the near term or using a NISQ device? And I think the answer is probably not in 1D scattering. These MPS methods are just too good that any kind of realistic or useful simulation, at least in the near term, we're always going to be able to do better with matrix product states. But I think the outlook is pretty good as we go to 2 dimensions and definitely in 3 dimensions. I think this could be an area where in the next couple of years, we can start to see simulations that it's very hard to reproduce using any classical method. And what's exciting and what Roland said earlier is this actually aligns very well with the IBM roadmap over the next couple of years. So up until now, we've had these heavy hex connectivity devices, which for a lot of purposes allow you to do 1D connectivity. Maybe you can do kind of quasi 2D, but 2D connectivity has this 16x overhead in 2-cubic gates, so it's not really that feasible. But by the end of this year and moving into 2026 and 2027, we're going to have these 2D chips that are really going to allow us to kind of natively and efficiently do these 2D simulations. And maybe we can start to see some quantum advantage in these scattering. So with that, I'd like to thank you all for listening and thank my collaborators on this project, Nikita, Mark, and John, and be happy to take any questions.